Okay, now this next topic to do with polarity really encompasses a very important concept in chemistry, and that is of electronegativity. Now, this is a term that you should be able to define. It's a measure of attraction an atom has for the electrons in a shared bond. So these two electrons here, represented by this line, are shared by chlorine and hydrogen. It's a covalent bond, if you remember. Now, the attraction the chlorine has for those electrons is stronger than the attraction that the hydrogen has. Now, this is something that was found out through observation and experiments, and numbers have been assigned to this to try and work out how strong the attraction is. So these electrons don't necessarily just sit in the middle. In some respects, you could look at it that they're being pulled more to one atom than the other, although electron movement and interactions is a lot more complex than that. But a table can be made of electronegativity to give us some idea of the relative strengths of the different atoms, the strength of their attraction for these electrons in a shared bond. Okay, and this table shows it. And if we look at it, as you go across a period, it increases, and as you go up, okay, and that should kind of make sense. The smaller radius atoms, there's less distance between the nucleus of the atom and the electrons that they're sharing, and as you go across you get more and more protons being added, so they get stronger as you go across in terms of the attracting power. So you can kind of do one final arrow to show that general kind of trend, that as you go up in that diagonal kind of way, that you get stronger. So really what you should appreciate from this is that fluorine is the strongest, and NOF, these three are particularly strong, and as is chlorine and bromine. So if you have a general idea that as you go across and as you go up, electronegativity increases. But to all intents and purposes, the examples you'll be presented with should be straightforward. You don't need to memorize this table. Okay. Now, when we look at these molecules, this is supposed to be O2, H2, N2, and Cl2. Now, in each of these cases, the O is exactly the same as the O, obviously. So the attraction that they have for these electrons in the shared bond in the middle and here is going to be exactly the same. It's really like two people of the same strength, pulling on a rope in a tug of war. You get no movement. There's no movement of the electrons to either side because they're equally strong. So when the atoms are the same, as in each of these cases, the hydrogen, the nitrogen, the chlorine, the electrons stay exactly where they are. Although again we'll find out later that that's not quite true, but just to understand polarity, just think of them staying there, and that means we have a term for that when there's no, we call it being non-polar, because the electrons aren't pulled one way or another, and that'll make more sense when we look at another case. Now in this case we've got HCl. Now Cl is a more electronegative atom than hydrogen. That means the electrons will be pulled towards it, and so instead of the electrons being close to the hydrogen, they'll be closer to the chlorine. They're not going to be in the middle, and that creates a very slight charge. Okay, we call it, it's a delta negative and a delta positive. Okay, so sometimes we do that as well. So this here, important, you should have some idea of how to draw this, and you should know, for instance, that NOF and chlorine are fairly electronegative atoms. So that's a little bit negative, and in this one, the oxygen, that's going to pull the electrons towards it. So that means that's going to be a little bit negative and a little bit positive. Now, because we have a slight positive and a slight negative, that has a term, it's called a dipole. All that means is that we have two poles, a positive and a negative. This is not an ionic charge. They have not gained or lost electrons. This is just a slight negative and a slight positive. It is not ionic. That needs to be stressed. Okay. So when we get this slight negative and a slight positive, we have a name for it. We call it being polar. Okay, so in the previous example when we had H like this or Cl like this, because there was no dipole, in that case that was non-polar. Okay. Now these aren't necessarily all complete molecules, although one of them is. They're just to represent two different atoms that are bonded together, and whether you can predict whether a dipole will exist. Now, in this case, obviously, you don't need to know the electronegativity. Basically, all you need to know is that if this atom is different from this atom, it's going to be polar. So how about this case? Well, obviously O is different from H, so that's going to be polar. And if we look at HF here, again, is H different from F? Yes, it is, so that's going to be polar. Is S different from S? No, it isn't, so that's going to be non-polar. Is N different from H? Yes, it is, so that's going to be polar. Is Br different from Br? Is it going to be polar or non-polar? It's going to be non-polar because they're the same. Now this is the one that you need to know about, because in some cases the difference in strength between the two atoms is so small we consider it to be non-polar. Now this is the one you would be absolutely expected to know. Carbon and hydrogen, the difference in electronegativity is not that great, so essentially we consider it to be non-polar. Okay, so that's the only one you're expected to know that's a little unusual. Alright, so that's looking at polarity and electronegativity with two atoms. Now molecules often are bigger than two atoms. They're often 3, 4, 5, much more. So the next video tutorial will be on how do you understand polarity in bigger molecules, and that's reasonably straightforward as well.